Good morning, everyone. So welcome to my YouTube channel, Maths Program. So today we are going to see ninth lecture on Riemann integration. In last lecture, we have proved some necessary and sufficient condition for Riemann integrability. Now we will derive results from the result which we have done in last lecture. So let us start today's session now. So first result is we are calling it reduction 1. Why we are calling it reduction 1? Because we will derive this result from the results we have done in last lecture. Let f from closed interval AB to R be a bounded function. Then f belongs to R AB means f is Riemann integrable if and only if there exists I belongs to R. Okay, such that given any epsilon greater than 0, there exists delta greater than 0 with any partition P of AB. We have U LPF is less than equal to I less than equal to UPF and LPF minus I less than epsilon and UPF minus I less than epsilon. Okay. So let's go this. First, assume that f is Riemann integrable. It means f belongs to R AB. Okay. Then by theorem 1 of Riemann integration, lecture 8, we have lecture 8 given. Okay. Given any epsilon greater than 0, there exists delta greater than 0, such that so here in the statement of theorem, you write one thing. Any partition, there exists a delta greater partition of AB there exists a delta greater than 0 with any partition P of AB norm of P less than delta we have this one. Okay. And we have this one. So first assume that function is Riemann integrable by theorem 1 of last lecture. Given any epsilon greater than 0, there exists delta such that UPF minus LPF is less than epsilon for any partition P of AB with norm of P less than delta. Okay. Since F is Riemann integrable, we have integration A to B fx dx is less than UPF and it is less than LPF. Okay. So put for any partition P of AB. Okay. Now put I. So put I is equal to A to B fx dx and then it belongs to R. Then LPF is less than UPF for any partition P of AB. Observe that because I is in between this, so we have the distance of LPF minus I is less than equal to distance of UPF minus LPF. Okay. And UPF minus I less than equal to UPF minus LPF. Okay. But this is less than epsilon, this part, and this part is also less than epsilon. Okay. So this implies LPF minus I less than epsilon and UPF minus I less than epsilon. For any partition P of closed interval AB with norm of P less than delta. Okay. So one part is done. Now assume that converse statement of the given theorem is true. Okay, is true, then okay, then we have given any epsilon greater than 0, there exists delta greater than 0 such that LPF minus I less than epsilon and UPF minus I less than epsilon by 2 for any partition P of AB with non less than delta. Okay. Next, what we have? We have UPF minus LPF. Okay. Now you add and subtract Fi. Okay. So what we have? UPF minus I plus I minus LPF. Okay. So how we can write this one? Because this is absolute value, so it will not affect anything. You can write like that. You can write this LPF minus I. So this is less than epsilon, this is less than epsilon. So this is epsilon. So this implies UPF minus LPF is less than epsilon for any partition P of closed interval AB with norm of P less than delta by theorem 1 of Riemann integration lecture 8 okay. We have F belongs to R A. It means F is Riemann integral. Okay. So again we are applying theorem 1 of last lecture. Okay. Lecture 8. So this theorem is true. Now reduction 2. Reduction 2. What is that? Okay. Let F closed interval AB to R be a bounded function. Okay. Then f belongs to RAB. It means f is Riemann integrable if and only if there exists I belongs to R and a partition there exists I belongs to R such that given any epsilon greater than 0, there exists a partition P of AP with LPF minus I less than epsilon and UPF minus I less than epsilon. So we'll do prove this proof. First, assume that f is Riemann integrable. Okay. Okay. Then by theorem 2 of Riemann integration lecture 8 okay given any epsilon greater than 0 there exists a partition P of AB with UPF minus LPF is less than epsilon. Since f is Riemann integrable, we have LPF need to be FFTS UPF for any partition P of AB. Okay. So put I is equal to A to B FFTS integral of F. So this belongs to R. Now, because now LPF is less than equal to I UPF for any partition P of closed interval AB. Okay. Observe that because I lies between LPF and UPF. So what does it mean? It means LPF minus I is less than equal to UPF minus LPF. That is less than epsilon. And UPF plus I less than equal to UPF minus LPF less than epsilon. Okay. Therefore, there exists a partition therefore given epsilon greater than 0, there exists a partition P of closed interval AP such that LPF minus I is less than epsilon and UPF minus I less than. Okay. Now assume that convergence statement of theorem is true. Next, assume that the convergence statement is true. Okay. Then, given any epsilon greater than 0, there exists a partition P of AB such that LPF minus I less than epsilon by 2 and UPF minus I less than epsilon by 2. Okay. Then UPF minus LPF is equal to UPF. You can subtract I and you can add I. UPF minus I minus LP. So what is this? We can write, because this is absolute value, so I can write LPF minus I. Now this is less than epsilon by 2 and this is also less than epsilon by 2. So we are adding this and this is strictly greater. Okay. So what is this then? This is. Therefore, given epsilon greater than 0, there exists a partition P of closed interval AP such that UPF minus LPF is less than epsilon. Now by theorem theorem 2 of Riemann integration lecture 8. We have F belongs to F is Riemann integral. F belongs to R. Okay. So this theorem, this result is also proved. Okay. So now move to next theorem. Let F close interval AB to R be a bounded function. Then F belongs to R A B implies alpha F belongs to R A B for any alpha belongs to R. Okay, and the Riemann integration of alpha F is equal to alpha times Riemann integration of okay. So let's prove this. Proof. Assume that F belongs to R A B. Since alpha belongs to R, we have either alpha is non-negative or alpha is strictly less than 0. It means negative. So case first, alpha is greater than 0, greater than equal to 0. Okay. Let P is equal to A x naught, x1, x2, xn minus 1, xn is equal to B. B a partition of closed interval A. Then supremum of alpha F such that X belongs to xi minus 1 xi is nothing but, because alpha is non-negative. If alpha is non-negative, this is equal to alpha times supremum fx. X belongs to xi minus 1 xi. So what is this? Alpha times capital Mi. Okay. and infimum of alpha fx x belongs to minus I to xi close interval. This is nothing but, because alpha is non-negative, it will come outside. Infimum of fx x belongs to xi minus 1 to xi. So what is this? Alpha small mi. Okay. Now, what is this? Now, what is UPF? Now UPF, UP alpha F, what is this? This is summation I goes to 1 to n. What is the supremum of alpha? Alpha F, this is alpha capital Mi delta xi. So I can take alpha outside. Mi delta xi. Okay. So what is this? This is alpha U UPF. Okay. Okay. And what is it? So what does it mean? So this implies the upper integral a to b alpha f x dx. What is this? This is alpha times a to b okay. What is this? So this implies, let me write properly. So this implies a to b upper integral fx dx alpha f dx is equal to infimum of UP alpha f. P is a partition of closed interval AB. But this is nothing but, because UPSC, this is infimum of alpha UPF. Because this is the UP alpha F is equal to alpha times UPF. P is a partition of closed interval AB. So alpha will come out. This is infimum of UPF. P is a partition of closed interval AB. But what is this? What is this? This is lower integral of f. This is lower integral of f. Sorry, upper integral. This is upper integral. But f is Riemann integrable. So this will be equal to So this implies A to B alpha fx dx is equal to alpha times A to B fx dx. Since f is Riemann integrable, therefore A to B fx dx is equal to A to B fx dx is equal to lower integral also. Okay. So that is why this is equal to this. Okay. So we have calculated upper integral, that is alpha times integral of f. Okay. And similarly, we will calculate LPF of alpha f. What is LP alpha f? That is also supremum of lower integral. We will also calculate lower integral. Okay. So this will imply lower integral is A to B fx dx is equal to supremum of what is this? Alpha f x dx. What is this? Supremum of LP alpha f. P is a partition of AB. Okay. Now solve it. So LP alpha f is nothing but alpha times LPF. So this is equal to supremum. This is alpha times LPF. P is a partition of closed interval AB. But alpha will come out. This is supremum of LPF. P is a partition of AB. But what is this? This is nothing but lower integral of f. But f is Riemann integrable. So this implies A to B lower integral alpha f x dx is A to B f x dx. Okay. Let's say this equation number 2. And first you say this equation number 1. So from 1 and 2, we have A to B alpha f, upper integral of alpha f is equal to lower integral of alpha f x dx is equal to alpha times A to B f x dx. Okay. So this implies Because lower integral is equal to upper integral, it means alpha f is Riemann integrable, and the integral of alpha is nothing but alpha times integral of fx. So this implies alpha f belongs to R A B, and integral of A to B alpha f x dx is equal to alpha times A to B fx dx. So this is proof. Okay. Now we have proved it if alpha is greater than equal to 0, but one case is remaining. If alpha is negative, case 2, alpha is strictly less than 0. Then what will happen? Then what will happen? In this case, what will be UPF? UPF will be equal to, what will be? Then what will be the supremum of alpha fx if x belongs to minus xi minus 1 to xi? Then what will be this? This will be supremum of alpha fx x belongs to xi minus 1 to xi. So alpha is negative. Once you take alpha outside, here supremum becomes infimum. Okay. So that is the difference. If you are taking negative here, if you will take alpha outside, this will become infimum. But once alpha is non-negative, this will not affect. It will remain as it. But here alpha is negative. That is why it is when I am taking alpha outside, the supremum is changing to infimum. Okay. So this is equal to alpha times mi. Okay. And what is infimum of alpha f x belongs to xi minus xi2? This is infimum of alpha fx x belongs to xi minus 1 to xi. So I am taking alpha outside. Then infimum will become supremum. Okay. So what is this? This is alpha capital Mi. Now, what is the U P alpha F? What is that? This is nothing but I goes to 1 to n. Now, supremum of alpha F on xi minus 1 to xi interval is nothing but alpha times small mi. Okay. So you take outside alpha. So what you will get? So this is alpha summation I goes to 1 to n mi delta xi. Now what is this? This is nothing but LPF. And so this will implies that upper integral alpha fx dx is equal to that is supremum of UPF infimum. This is infimum. P is a partition of AB. Sir, what is this? This is infimum of, so here, this is alpha f x dx, upper integral of alpha. It is, so this is alpha LPF, because we have proved that UPF is equal to P is a partition of AB. Now alpha is here negative. If I will take alpha outside, infimum will become supremum. So this is equal to alpha take outside, so this will become supremum. LPF P is a partition of closed interval A. Now what is this? This is lower integral of F. This is lower integral of F. A to B. But F is Riemann integrable. I can write this integral of A to B Fx dx. Okay. So what I got? I got this one. This implies A to B Fx A to B alpha Fx dx, okay, is equal to alpha A to B Fx dx. Let's say equation number 3. So and now calculate LPF of alpha F. And what is LP alpha F? That is I goes to 1 to N. Now what is infimum of alpha F over the interval minus x I minus 1 to xi? That is alpha capital Mi delta xi. So take alpha outside. So take alpha outside, what you will get? So take alpha outside, alpha summation I goes to 1 to N Mi delta xi. Now what is this? This is UPF. Okay. So this implies lower integral is equal to supremum of LP alpha F. P is a partition of closed interval AB. Okay. So this is supremum of, but this is alpha times of UPF. P is a partition of closed interval AB. So I can take, if I will take, because alpha is negative, if I will take outside, it will be infimum of UPF. P is a partition of closed interval AB. Okay. But this is nothing but then what is this? This is upper integral of F. But F is Riemann integrable. Then what is this? Okay. So this implies A to B lower integral F alpha F x df is equal to alpha A to B F dx. So this is equation number 4. From 3 and 4, we have what is happening? Because we have A to B alpha F x dx is equal to lower integral A to B alpha F x df, and that is equal to alpha times A to B alpha dx. Okay. So what does it mean? It means that because upper integral of alpha f is equal to lower integral of alpha f. So this implies alpha f belongs to RAB. It means alpha f is Riemann integrable, and the integration of alpha f is nothing but alpha times of integral of A to B f. Okay. This theorem is proved now. Okay. We have dealt with all the cases of alpha. Alpha non-negative and alpha is negative. Okay. Now I would like to write a corollary. What is that? Let f belongs to RAB. Sorry, f is bounded function. F is bounded function. F closed interval AB to R be a bounded function. Then f belongs to RAB. It means f is Riemann integrable if and only if alpha f is Riemann integrable for all alpha belongs to R such that alpha is non-zero. Okay. So all the non-zero alpha f belongs to RAB and only alpha f belongs to RAB. Let's see its proof, how it will work. Now, first, assume f belongs to RAB. Then by theorem, just the theorem we have proved. By theorem, we have alpha f belongs to RAB. Okay. For alpha belongs to R and alpha is non-zero. Conversely, assume that alpha f belongs to RAB. Okay. For all alpha belongs to R, alpha non-zero. Okay. Then again by theorem we have because alpha f belongs to RAB, so this will imply 1 upon alpha f belongs to RAB. Okay. For alpha non-zero, so this implies, so this will be cancelled out. So this alpha will be cancelled out. This belongs to RAB. Okay. So result is proved. Okay. Let's say it is corollary 1. So we can write another corollary. Corollary. Corollary 2. Let f close interval AB to R be a bounded function. Then f belongs to RAB if and only if f belongs to alpha f belongs to RAB for some alpha belongs to R and alpha is non-zero. Similarly, we can prove it. Proof. How we will prove it? So let alpha is some non-zero. Then what we have? F belongs to RAB implies alpha f belongs to RAB. Now alpha f belongs to RAB implies 1 upon alpha f, that is f belongs to RAB. Okay. So this implies for alpha non-zero. Okay. Therefore, R belongs to AB if and only alpha f belongs to R A B or some alpha belongs to R, alpha non-zero. Okay. Alpha is not equal to 0. So we will add with a remark. Let f close interval a b to R be a function if alpha f is RAB in RAB for some alpha belongs to R is f belongs to RAB. It is true. It is true. Solution. Answer is no. No. Because you take, let f be a let f close interval 0, 1 to R be a Dirichlet function. So we have given example of a Dirichlet function. What is Dirichlet function? Okay. Be a Dirichlet function. What is this Dirichlet function? How it is defined on close interval 0, 1. We always take fx is equal to, it is 1, or you can take 0 also if x belongs to close interval 0, 1, intersection 2, 0. Okay. If x belongs to close interval 0, 1, intersection R minus 2. Okay. You can take Dirichlet function. Okay. So I am writing this function. Do not write here Dirichlet function. You directly let f be a function, a function defined by this. So this function is not Riemann integrable. This function is not Riemann integrable. Is not Riemann integrable. That is why it is not belongs to R01. Now take alpha is equal to 0, then alpha f. What is this? What is alpha f function? Alpha f function, what is this? Zero f. This is 0 function. But 0 functions are always Riemann integrable. Okay. So the answer of this function is no, because you can have alpha f Riemann integrable function, but f may not be Riemann integrable function. Okay. So answer is no. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Thank you very much for today's lecture. Like, share, comment and subscribe my YouTube channel. Thank you very much. We will see you in next lecture.